homework right here. Yeah.
Or did you do 3, 4, and 6, 8?
Yeah, 4. 3.68, can you tell me? We'll be doing capacitance today, but the boundary conditions and the actual, really, the del squared V equals minus rho V over epsilon naught is important.
1 meter long carbon pipe is altitude diameter 3 centimeters and outer diameter 5 centimeters.
All right, so we have a long rod, and we have an inner diameter A and outer diameter B. And what's the length on?
1 meter long.
Okay. Go ahead.
Inner diameter 3 centimeters, outer diameter 5 centimeters.
A was 3 centimeters, and B equals 5 centimeters. Is it made of carbon, you said?
Yes.
All right, so I'm assuming it's hollow, and it's carbon here, is that right? All right, now how do they want the resistance lengthwise or from the inner radius to the outer radius?
It's cut in half lengthwise.
What's it?
Lengthwise.
All right, this is a straightforward problem. You have to know the conductivity of this material. So the conductivity of, he says carbon, right? And what is that? That I don't know off the top of my head. Because there's several forms of carbon. There's graphite, there's diamond, there's all these forms. He has to give you, does he give you a conductivity? Say again? Does anybody have that? Did anybody look at this one? This is a straightforward problem. Did somebody just find the conductivity of carbon used in that problem? And it's probably graphite, but I'm not sure. Here's what it always comes down to. You see how it's going to have a constant cross section. All the current will be flowing along the lengthwise path. You all follow me? If you put,
It's a 3 times 10 to the 4.
all right. That's 1 over all meters or Siemens per meter. So if all the current is flowing down, I want to do this 2 different ways. Down this way. You see how it's constant cross section? Nothing changes, right? It's flowing in this hollow pipe that's between A and B. Everybody follow me on this? So the general formula for resistance, if it's constant cross section, is just L over sigma A. L is the length, sigma is the conductivity, and A is the cross-sectional area that the current's flowing through. Does everybody follow me? Now this is for constant cross-section. How many understand that? Right? So for this, it's going to be length over sigma, and what's the area going to be? Well, the way I do this is I always take the area of the outer radius, so that's pi b squared, correct? Then I just subtract the inner area. So the area right here that would be flowing through the cross-sectional area here would be pi with b squared minus a squared. So that means it's just going to be pi times b squared minus a squared. So L's 1 meter, sigma is 3 times 10 to the 4th, pi is pi. B is equal to 5 centimeters, A is equal to 3 centimeters. Could somebody just do this for me and tell me what that resistance is? Now that's along the length, right? It's not from the inner radius to the outer radius, but go ahead. You got a calculator? Okay, somebody just punch that into your calculator. Five squared, 25 minus 9. It's going to be 16 times 10 to the minus 4th. So it looks like 1 over 3 times 16, or 1 over, is that right? 1 over 48, I think. What did you get? Anybody?
5.3.
Say again?
5.3.
1.3?
5.3.
5.3? Anybody else? Is that right? Doesn't look right, but let's just see. L is 1 meter, sigma is 3 times 10 to the 4. Right? Now you have pi, you might be right, but let's just see here. Then you have b squared, well that's going to be 25 centimeters squared minus 9 centimeters squared, so that's going to be 16, and this is going to be centimeters squared, so it's going to be 10 to the minus 4. So unless I'm doing this wrong, it looks like it's 1 over 3 times 16 times pi. Y'all follow me on this, guys? What I'm doing here? Is that right? I mean, what's that value come to? I don't think it's not greater than 1. It's 1 over 16, 1 over 3 times 16 times pi, so 1 over 48 pi. Pardon?
0.0066.
Is that the answer in the solutions? Is that it? But that's all it is. And again, he's doing it lengthwise. He's looking at resistance along the length of it. Now, hear me on this one, because I like giving these kind of problems. So, leave that there. And actually, I'm going to redraw this. So now suppose I have this configuration. I have an inner conductor of radius A, and here's radius B, and it's going to be simply 1 meter high. But I'm going to metallize this inner conductor. So in here, we're going to have a metallic surface, and then we're going to metallize this outer surface here. And I want the resistance that would be between the inner conductor and the outer conductor. Y'all follow me? It's the tube, but now current's going to flow radially in this direction, not along the line. And if you look straight down the thing, it would look like this. I would have an inner radius A, an outer radius B, and current will flow this way. It's going to flow in the radial direction. Y'all follow me in this class? Now, to do this problem, you go through it the same way as you would any other problem you're calculating resistance. You assume one or two things. In this case, I'm going to assume the current. So this is plus minus V, and I don't know what that is, but I'm assuming the current I. Y'all follow me? Now that current has to flow from the inner surface to the outer surface, and it's going to be, the current density will just be a function of radial distance away. Does that make sense to everybody? So if I look at this, I'm assuming I've got a current I. If I go ahead and I put this surface here, it's like a Gaussian surface at radius rho, and I want the current density there. Remember, I made the height 1 for a reason, 1 meter high, because that way I'll get the per meter resistance between the inner and outer conductor. So I'm assuming I, now I get J equal to I over, well, it would be the perimeter, or 2 pi rho, times the height h. I made h1, which is nice, and this would be a rho. You all follow me on this, guys? Right? How many see this right here and understand? Now after that, the next thing you have to do, after you get I, J, then you get E, right? E, of course, would be equal to J over sigma, so now it's this. It's I over 2 pi rho h sigma in the a rho direction. Word of caution here, that value of sigma doesn't have to be a constant. It could be a function of radial distance. Y'all hear me on this one? It could be a function of radial distance. I like to give problems like that on exams and quizzes. Y'all hear me? I like to give problems like this, cylindrical or spherical, that have conductivity as a function of distance, or range, you might say. All right, now I have E. What's the final step always going to be? V. How do you get V?
Integral.
Integrate E from the inner to the outer surface, right? And it's always positive. So I'm going to go ahead and integrate this E, which is I over 2 pi rho, right? And then it's times H. H is 1, so it doesn't matter, times sigma. I'm just going to leave this as a constant. I'll make it sigma naught here. That's in the A rho direction. Now I have to dot that with DL. DL is just going to be D rho, A rho. Because if you put the other terms in there, Z and phi, the dot product with A rho is 0. So I don't even bother putting it there. It goes from A to B. Okay. Here, A rho dot A rho is 1. So I really have I over 2 pi H sigma naught, right? Now I have to integrate 1 over rho. What's the integral of 1 over rho d rho class?
Natural.
Natural log, right? The more you interact, the better you retain information. It's a military trick, it's true, yes.
If we just wrote down that integral, then we kind of, if we write down integrals and skip the integration if we're going to answer, are we allowed to do that?
Well, you should show the answer, so I know you know what
No,
you're
the
doing.
answer, but like not the.
Yeah, the answer going to be what? Natural log, right? It's going to be B over A, right? I mean, you can put natural log of rho, evaluate from A to B if you want, but this is going to be the final form, right? Once you have that, now you have the answer. You tell me the conductivity and the height. I have the voltage. How do you get resistance? Anybody?
Divide by I.
Divide by I, you see how the I goes away right there? So this, right, would be the resistance between the inner and outer conductor. Just remember that. Now, any other questions about, I want to make sure I really underscore that fact. That's a simple problem. You can get the actual resistance from in to in or between inner and outer conductor. Any other? Sorry. All right, my bad. Other questions, anybody? It's really warm in here.
Yeah.
Humid, I should say.
Can we do 3.62?
Yeah. Is this a boundary value problem or what kind of problem?
Boundary conditions.
What is it?
Boundary conditions.
Okay. We'll do at least one of those.
So what do you do if it varies?
It just, whatever, like if it's rho or R, you just multiply
Alright.
the sigma into it, and then you just have to,
3.62,
the
go ahead.
integral will be different is all. For y is less than 0, epsilon relative 1 equals 4.
And this is going to be, this is the y-axis, this is going to be color. Go ahead.
For y is less than epsilon relative 1 equals 4, and E1 equals 3ax.
Oh, right, so this is in the region below y equals 0, right?
Yes.
Okay, what is E? Go ahead.
And E1 equals 3ax plus 6 pi ay plus 4az
6 pi y.
volt per meter.
Plus? What's next?
4az.
4 AC?
Mm-hmm.
Okay.
And then at y equals 0, rho s equals 0.25 nanocoulombs per meter squared.
Rho S, what? Say again?
0.25 nanocoulombs per meter squared. And then if epsilon relative 2 equals 5.0 for y is greater than 0, find E2.
5 1. Okay. This is a classic problem. It's just making sure you're straight with things. Remember what I said with boundary conditions? E tan 1 is E tan 2, right? That will always be the case. You with me on this, class? Now, what is the tangent value of the field here? Remember, the variation in the actual permittivity happens at y equals 0 for all x for all y. You all follow me in this class? Now, I mean all x, all z. So in this case, x, y, z would be out of the board the way I've drawn this. Now, the tangent components are always going to be parallel to the plane of separation. The plane of separation is really going to be xz. Can you all see it the way I've drawn it? If you look at that, the tangent value of the electric field would be Ex and it would be Ez. Do you all follow me, class? How many see this right here? All right. It has to be in the plane of separation. So if you look at this, the tangent components are gonna be AX, right, and they're gonna be AZ. So I can say, based on that, the E field, the tangent components of the E field in region 2 are just gonna be the same, which are 3AX, right? That's plus 4AZ. And that's volts per meter, I'm betting, right?
Yeah.
All right, so that's done. Now we need to get the normal component, right? We have to get d normal 1 equal to d normal 2, but there's a caveat because there's a surface charge density, right? So now, if I call this region, well, he calls this region 2 here, or 1. So if this is region 2, and this is region 1, then a unit vector going from 2 to 1, that would be the normal vector, would actually be minus A1. Does that make sense to everybody here? Because the way he has it in the book, he has 2 and 1, right? But he has 2 below 1 in the book, but this is the formula. Y'all follow me in this class? So then it says what? It says if I take A normal, or A21, that's a unit vector from 2 pointing at 1, and I take that and I dot it into D. In this case, it's going to be D1 minus D2. I think he has it this way in the book. That would be rho S. I'll give you a page number on that because I actually don't know if he uses it norms. I think it is 2-1. So this is in, let's see.
Yeah, so like, if it was like, you know, you take everything out because it's not, it doesn't involve the interval.
All right, this is on the
If
bottom
sigma
of page
like was rho,
188.
if it was like
And
1
it
over
shows-
rho,
y'all
or just
follow
rho,
me in this class?
and it was like 1 over rho
Now,
squared, then you
here we
just
are
put the
this
rho
one.
on top
We'll
of it,
take
and
a
they
look
would
at
cancel
this.
out. It just, you would involve it in whatever
We
the
have
piece is inside the interval,
A21,
because it's,
A21 is
in
minus
terms of
A1. So
what
I
you need
have
to integrate now.
minus A1
It does.
divided with, now just listen to this. You see how the only D field component that matters is Y. If you had a DX and a DZ, the dot product with AY would be 0. Do you all follow me on this, guys? Let me see this right here. All right, so what you can do is simply put, this is the, we've got the D field in region 2, don't we? The D field in region 2, the normal component. The normal component would be 6Y, AY would be the E field, right? So the E field in region, region 1. E field in region 1 would be equal to 8AY, or 8 pi volts per meter. You all follow me on that? Now please watch this. You with me? And you remember that D is equal to epsilon E in general, correct? Right? We need the D field. You all follow me? So if we need a D field, we can say the D field in region 1 that's normal is going to be this E field times epsilon relative in region 1 times epsilon naught. So that E field is going to be 8 pi. Epsilon relative in region 1 is 4, right? And then it's going to be times epsilon naught. So that goes, and that is in the AY direction. I just put it AY here for completeness, but it's really. So when I take this, it would be times, 8 times 4 is 32 pi epsilon. And then it's going to be minus D in region 2, and that would be D normal in region 2 AY. Both of these are AY, so that AY component goes out. It's equal to rho S, and rho S was 0.25 nanocoulombs times 10 to the minus 9 coulombs per meter squared. Now, if you look at this just for a second, I just want to make sure you, yes, sir?
It's a 6, not an
What is that?
8. The Y one is
Oh.
a 6.
6, my bad. This is 24, right?
Yes, sir.
All right, when you take a look at this, we'll just flip these around because the minus there is going to cause them to just change places here. So it's going to be D normal 2 minus 24. minus 24 pi epsilon naught is equal to, call it 2.5 times 10 to the minus 10th, right there. Now to get d normal 2, that's going to be 2.5 times 10 to the minus 10th, and it's going to be plus 24 pi epsilon naught. Now that would be the D field. We could calculate that. Does he ask for the E field in region 2?
Yes.
Okay, so that's the D field in region 2. Does everybody follow me on this? And to get the E field, what do we know? The D field, right, is epsilon E, correct, class? So the normal component of the E field in region 2 would be this, but that would be epsilon in region 2 is 5, right? So it would be 5 epsilon naught right here times the E field in region 2 as the Y component. Call it EY2 right here. So if you take a look at this, what I'm going to do, if you have this, you all follow me what I've done here? I just followed the formula for beta, right? Now look just what happens here when I want, this is going to be the electric field that's perpendicular. We're going to add it to that prior field. When you do this, you divide all this over here by 5 epsilon naught. So it's by 5 epsilon naught. And you can see the epsilon naught cancels here, but what do you get for this value then? Can somebody do that for me? You're going to get 24 pi divided by 5 plus 2.5 times 10 to the minus 10th divided by 5 epsilon naught. I can't do that in my head, but you can tell me what that is. But that would be the answer, I believe, in this book. Doesn't he do it this way, class, in the solutions?
He does it the long way.
That is the I've got the E fields, right?
Yeah, he does it like the directions like every single way. Like he he goes to like the E point on the solution.
For the E field in region 2, he should have 3AX plus 4AZ. Do you see those two numbers?
Yeah.
All right. Now this would be the Y component right here. You're going to have to tell me what that is, but it'll be the same. You do it right. I can't tell that off the top of my head. I'm not sure. Anybody? Are y'all following me when I'm doing this? I'm literally just going by the exact formula. I'm not changing anything. Is that the right answer, guys?
What's epsilon naught again?
8.854 times 10 to the minus 12. Go ahead.
What's in the bottom?
5 epsilon naught. Remember, this was 1 EY, so we have 5 epsilon naught times D, right, which we had over there. We have to divide that by 5 epsilon naught to get the actual value of the E field. Y'all follow me on what I'm doing? All right, is that, it's right, I'm sure. Can you confirm it? Confirm or deny? Is that what you got? No, I mean, did you come to, you didn't punch it in? Anybody calculate this thing? I have a feeling it is right.
Yeah.
It is?
It's the same.
All right. All right, we'll move on. But that's the kind of stuff, you have to get familiar with the formulas, that formula he put in the book. The way I do it would be a little different, because I know that without any charge density, D normal 1 is D normal 2. That's the way I usually do this. If there is a charge density, if there is a D field, if there is a charge density, then I have to see the additional amount of the D field caused by that charge density in region 2 and in region 1. Subtract it from one, add it to the other. That's the only thing. But that's how I would do that normally. Yeah.
And for how you found the E1, because you took out the 6 pi, it's just because that's the only one that in the direction that matters for like the Y.
What does it always say? That the tangent value of the field, tangent is always, if you talk about tangent to a surface, if it's the tangent to the actual carpet I'm standing, that's in the horizontal plane. If that was X and that was Z, it would be the X and Z component of the E field. Do y'all follow me? The normal component is perpendicular to the surface. So it's D normal 1 is D normal 2, unless there's a charge density. And then you have to take that A21, dot it in with D, it's really D in region 1, minus D in region 2. It's always the normal component. You take that and subtract it and set that equal to the charge density. That's how you would do it. They're not hard things to do. They're just, it's one of these things you have to be a good bookkeeper. You can't be careless. You won't make errors. Anything else? Any other problems you want to see done? Because I gave you some problems with the Laplacian, didn't I? The del squared Poisson's equation?
Yeah, I think that was the last one.
What's that?
It's the last problem you gave us.
All right. We might as well do it. Did you try this or not? How many tried these? If you didn't, it's so be it. But if you didn't try it, I'm going to warn you. This is the stuff that will hurt you right here. We're about to do. This gets a little more complicated. So go ahead.
Yeah, 3.69.
Go ahead.
For a coaxial cable of interconductor radius A and outer conductor radius B,
Go ahead.
and a dielectric epsilon relative in between, assume a charge density rho v equals rho naught over rho.
Oh, okay. So, hold on. We have an interconductor of radius A and outer conductor of radius B. Go ahead. And this is going to be a cylinder, right?
Mm-hmm. And the dielectric is epsilon, and then between them, and then the density is rho v equals
It's
rho
epsilon,
naught.
just epsilon?
Yeah, epsilon relative in
But there's
between,
a charge density.
and the charge density is rho naught over rho.
Rho naught over rho.
Mm-hmm.
Is that coulombs per meter cubed?
It doesn't give any values.
It better be coulombs per meter cubed. Now, this one's a little interesting. I'll tell you why. Because that charge, that's a bound charge density, that it's not moving, but it is a charge density he gave us. So now to do this, we're assuming it's invariant with length, because he didn't say it's a function of length in any way, just radial distance. So you start out by the actual formal Laplacian. If you look in the back cover of your book, that's going to be minus rho v over epsilon. Here, I guess he doesn't say what form this is. He just says it's epsilon, right? Okay. We'll leave it as epsilon. Now, if you look at this, this is cylindrical coordinates. You all follow me in this class? Cylindrical coordinates. It's invariant with z. And it's not a function of phi. So, and it's just arguments of symmetry. It is symmetric about the z-axis. It will only be a function of radial distance in terms of the variation in voltage. So because of that, it means this del squared operator is going to be what? 1 over rho, and it's going to be dd rho of rho times dvd rho would be equal to minus the charge density, which is rho naught over rho, and it's divided by epsilon. Now, I'm just literally taking this del squared operator from the back cover. If you look at the back of your book, very last page, and I've ignored the actual phi and z variations because it is symmetric about those two. There will be no voltage variation with phi or z. You all follow me? Yeah.
What is that in front of the dvd rho?
1 over, this is 1 over rho.
Right in front of the,
Here,
yeah.
that's rho. Do you have your
Oh,
book?
okay.
Look at the back cover of your book. And this is cylindrical. Do you see this form? Look at the very back cover. I think it's the last part on the lower corner, the cover of your book on the lower left-hand side. And you see it, no, flip to that, go to the very back, you're going front. Flip it. See it on the bottom there. Now, look at the bottom. Should be you see Laplacian. You see it?
Yeah.
Okay? Now look at
Cylindrical.
cylindrical form.
Mhm.
See, it's 1 over rho, dd rho of rho times dvd rho.
Mhm.
Everybody follow me on that? Now, I'll give you that for the first exam, so for the final, I may not. You should become very familiar with these forms. At least, well, maybe I will give it to you on final. These are things that's going to be second nature by the time you get out of ELEC. Go ahead.
So is that not a negative 1 over rho?
Pardon?
Is that not a negative 1 over rho?
Here,
On the left.
On the right
There's
side.
on this side, where are you getting negative from?
In the solution.
Well, no, it's negatives over here, right? You could put it on either side. If you want to put it on the other side, right? If it's, just multiply both sides by minus 1. Then the minus appears here, that becomes positive. It doesn't matter, right? If it's negative here, positive there, it's the same thing as positive here and negative there. You don't follow me on this, people? You see what I'm saying, sir?
What's it there? Both negative.
It's positive, right? If you got a negative on both sides, multiply by minus 1, you get a positive on both sides. It should be a minus on one side, a positive on the other. Are you good with this, guys? Okay. Now, let's go ahead and solve this. First thing I'm gonna do to make it simple, I'm leaving a negative over there. If I multiply both sides by rho, you see how this rho goes away. Everybody? Right? Now what am I gonna do? Now I multiply both sides by d rho, right? And when I multiply by d rho, I get d rho here, right? Y'all follow me on what I'm doing? Right? Now what do I have to do? Remember, that's a complete differential. Now I integrate both sides, don't I? With me, everyone? If I integrate both sides, what do I get? Well, if I integrate that side, I simply get rho times dv d rho equal to integrate that side, I get what? Minus rho naught over epsilon naught, right? And it's going to be that times rho. You all agree? Plus a constant, because this is an indefinite integral, plus a constant. Let's take a look at this. Do you all agree? Right? Now, what's the next step? Do they want the E field or do they want voltage?
They want an expression for both.
All right, we'll get voltage first. Now, I'm going to divide both sides by a rho. That gets rid of this rho, makes this over rho. Right, class? We don't know what that constant is, but y'all with me? Now what do I do? Well, I can almost stop right there for one reason if I don't want just the E field. You see how, remember the E field is what? It's minus the gradient of the voltage, isn't it, class? Right? Now, this is electrostatics. What is the gradient of the voltage going to be in general, cylindrical coordinates? It's dV d rho, right? Plus 1 over rho dV d phi. Look at the back cover, and this would be the actual gradient, right? And then it's going to be plus dV dz. I'm going to be AX, it would be A rho, A phi, AZ. There is no variation with Z or phi of the voltage. It only varies with radial distance, which means this right here is in fact minus the E field. And if I take that right there, I can say that this is minus the E field, which should only be in the radial direction, and that would be the right answer. Or I could say that the E field would only have a radial component, and it would be equal to rho naught over epsilon, and not epsilon up at epsilon, and it's going to be minus C over rho. That would be the E field. To get the final form of the voltage right there, I'd do another integration. Do y'all follow me? Right here. The next integral would do what? Well, it would put V as a function of rho would be equal to, and this is going to be C times natural log of rho, and I'll call this C1. Then it's going to be plus, or minus, I should say, minus rho naught over epsilon, right here, times rho, and plus a constant C2. Now, he should have a form like this in the book, in the solutions. You all see this, class? Take a look. He's going to have a natural log times a constant. He's going to have a term that's going to be minus rho over epsilon rho, and then he's going to have plus C2 for voltage. You see it? Okay? This is the form he's going to have for the E field, this, right here. There should be a constant there. Do you see it? Here's the thing. How would you evaluate that constant? What would you need to know? Because it's not specified in there.
A and B?
You would have to, in some way, shape, or form, say where V equals 0 is. And it will not be 0 at infinity, because this is an infinite amount of charge. So if you tell me that the outer radius is 0, that that voltage is 0 at B, then you can get a complete expression for both the E field and V. Both those constants will go away. But if not, did he leave in terms of just constants?
He plugged in A and B.
Oh, he did, okay. Well then, if he did that, then you can go down here, just hear me here. See, if he has VA, does he have VA and VB?
Yes. VA.
All right, so VA is the voltage at A, right? When the radius is A, you put in VA here, equals C, natural log of A, right? Minus rho 0 over epsilon A plus C2. That's the first equation. Second equation would be the same thing, only be V of B is equal to C times log B minus rho over epsilon times B plus C2. You subtract the two, you get the voltage difference between the inner and outer, and this constant will die, and you will solve for the other constant. Now, I think he does it that way, doesn't he? Let me just say this. The key to this problem, is getting this equation correct right here. And then going from here and just doing the natural progression. A common mistake that's made here, when you integrate, like when you integrate this, if you had dv d rho is equal to, say, rho. When you integrate both sides, unless they're definite integrals, then you get v of rho here. This would be rho squared over 2, but you have to add a constant because it's not definite. If it's a definite integral from the inner to the outer radius or something like that, then you just have to evaluate the outer and inner radius. Do y'all follow me, class? So make sure you add that constant when you do an indefinite integral. You know that from calculus, right? But they used to say always add Charlie or something like that when you took calculus. Okay, is that clear? All right. Now, today what I'd like to do is go through capacitance. Now, we've went through the boundary conditions. We went through finding a value of resistance, and we went through solving this del squared business. Now we're going to go ahead and talk about capacitance, which you've had before. So if we're trying to determine the capacitance between any two plates, the only way to do it is begin by assumptions. Let me go through this just like we did when we did resistance. Remember, for resistance R, what we did is I typically assume I get J. From J I get E, which is simply J over sigma. And then from there I get V, which is equal to the integral of E dot dl. And finally, to get R, it's V over I. The I assumed here will cancel. That's the method. Everybody with me? For capacitance, it's very similar. I want to add one other thing too. Usually, the actual progression this way is the best, but you can also assume V, then get E, then get J, and then get I. All right? That's another thing. Usually, it's easier to do it this way. Now, with capacitance, we talk about capacitance. The normal way to do it is assume Q. You don't have to do it this way, but it's a lot easier. After you assume Q, you get D. Well, D is always going to be Q over the surface that the flux would be penetrating. This is Gauss's law, all right? So highly symmetric problems we use this for. Everybody with me on this? After you get D, then you get E, and E is simply what? D over epsilon, correct? Once I have E, then I get V, which is equal to the integral of E dot dl. And, I mean, you can put a minus sign here, but frankly, you can go from A to B if you want. But it's always going to be positive for capacitance. And then, remember, the charge Q is equal to C times V. It's the voltage difference between the inner plate and outer plate, or between any two plates. That's equal to the charge on one plate divided by the voltage of the capacitance, where C is equal to V over Q. I'm going to remember doing that kind of thing in physics. All right, when you had physics, one of the big things they usually did is they went through how you determine the capacitance for typical shapes. Yeah.
Isn't that Q over V?
Yes, yes it is. My bad, Q over V. Q over V, sorry. Q over V. So I'm going to go ahead and do a classic problem. There's a couple. I'm going to start with probably one of the most classic problems is this. It's a spherical problem. So we have a spherical capacitor. We have an inner radius of A and an outer radius of B and some value epsilon. Now I want to warn you, epsilon can be a function of radial distance. It doesn't have to be a constant. For this case, we're going to assume it's a constant. So if you think about it, there's an effective capacitance between the inner and the outer surface. Assume it's metallized on A and metallized at B. Do y'all follow me, class? Y'all can visualize that, right? So if I assume a Q, I'll do it over here. I'm going to put a Q on the inside. So all through here, we're going to assume it's Q. Now, next thing, if I assume Q, and then I come out at distance R from the center, and I put a surface there, a complete spherical surface. I know the integral of d dot ds over the closed surface is the charge enclosed, which is my Q. I assume that. Isn't it, class? So if I wanted the value of d, it would be in simply the radial direction of dr, and it would be Q over the surface area of a sphere. What's the surface area of a sphere, people? In radius. 4 pi r squared, right? Isn't that right, class? You've got to know this, by the way. This is not, you're not going to get by this course unless you know these things. Surface area of a sphere is 4 pi r squared. Volume is 4/3 pi r cubed, right? But 4 pi r squared is the surface area. So now we get 4 pi r squared AR, if you'd like that, and that would be D field, right? Now, I went from Q to D, now I need E. How do I get E? Just look at it, class.
Divide by epsilon.
Divide by epsilon. So now to get the E field, and I'll put it up here. The E field itself would be the D field by epsilon. Here, the actual value of epsilon is constant, so it's Q over 4 pi epsilon, whatever that value is, right? And then it's going to be r squared AR. That's a point charge, isn't it? That's the electric field from a point charge. Go ahead.
What is, I'm just curious, what is the S in DS?
Surface, differential surface. DS, differential surface. All right, and the reason it's a differential surface, not an area, is because that surface has a vector sense to it, all right? It's area times a vector sense, which is radially outward. That's all it is. Okay? Now, once I have E, I need to get the voltage between the inner and outer conductors. So that voltage would be the magnitude of the integral of E dot dl. And that means it's simply going to be equal to the integral of Q over 4 pi epsilon r squared AR dot, and this is going to be AR dr, and it's a magnitude right here, so you can go from A to B if you want that way, and that's going to be Q over 4 pi epsilon, and then it's going to be simply 1 over the outer radius, or 1 over the inner radius, A minus 1 over B. That's the voltage, VA or VAB, oh, V, just V here. So that's the voltage difference between the inner conductor and the outer conductor. Now, to get the capacitance for this one, it's simply going to be the charge, which was assumed Q, right? Is everybody following me on that? Can you all follow me how I obtain the voltage? With me, I simply integrate the E field between the inner and outer conductor. Now to get the capacitance, I have to divide charge by that. And you can see what happens here. This is going to be Q, that's going to be 4 pi epsilon naught, right? Or 4 pi epsilon, just epsilon. And then it's going to be times 1 over A minus 1 over B. The Q's will cancel, and you get simply 4 pi epsilon, 1 over A minus 1 over B. And that is the capacitance between the inner and outer conductor. Can everybody follow me what I've done? I've assumed Q, got the D field, it's highly symmetric, it's easy to get. After that I get E, then I integrate E dot dl from the inner to outer conductor. Here's where people mess up. They won't remember this, they memorize these formulas. It does you no good to do that. You have to know the method to obtain it. And here's why. Because if this epsilon is a function of R, all of a sudden that integral is not going to be the same as it was. So, for instance, if epsilon here call this epsilon naught times r, which would make this r cubed. Y'all follow? If epsilon was epsilon naught times r, then it would be a 1 over r cubed integration. Do y'all follow me on that? Well, 1 over r cubed is what? Well, that's minus 1/2 1 over r squared evaluated from the inner to the outer conductor. It's a different form. It gives you a different capacitance. Does everybody hear me on that one? Now here's one nice thing about this that you'll thank me. Anytime you have, and let me just do it right here, just finish up with this point. But listen, it won't matter, it will not matter the geometry, but anytime you have two plates, and I'm just going to use a spherical case, but it won't matter what they look like. If you have a given, let's say inner radius, say outer radius, if there's a given conductivity and a given permittivity, if you talk about the capacitance between these two plates or the resistance between these two plates, y'all hear me? There would be an effective capacitance right here. I love this problem, by the way. An effective resistance. There would be some capacitance and some resistance, right? If you have a given epsilon and a given sigma. But the relationship between capacitance between those plates and resistance between those plates will be equal to epsilon over sigma. If epsilon and sigma are constants, not if they're variable. If they vary with radius, this is not true. But y'all hear me on that one? What does that mean? If you know the capacitance, you know the resistance. If you know the resistance, you know the capacitance. For any two sets of plate, they could be cylinders, right? Cylinders, they could be spheres, they could just be planar. You try that out, and it's in his book, but it's really a nice trick. Which means if you got the capacitance, you got the resistance. If you have the resistance, you have the capacitance. Y'all hear me? Now, I just showed you what the capacitance was right here between the inner and outer plates, right? If you wanted the resistance, we did this problem, I don't know if you remember. The resistance, I said, was going to be equal to, it would be epsilon over sigma c. So it's epsilon over sigma times c. Look at that. That's epsilon over sigma, and that's c right here. So if you divide by 4 pi epsilon naught, or 4 pi epsilon, whatever that is, and that comes upstairs. Now the epsilons are going to cancel, and now I have really 1 over sigma divided by 4 pi times 1 over a minus 1 over b. That's exactly what we calculated it to be earlier. When we assumed I, got j, got e, got v, did v over I. You check that. I'm going to give you a bunch of problems on this. For Friday, you're going to get a quiz. It will be targeting capacitance, all right? I'm going to give you a capacitance slash resistance. You got me on that one? It's either resistance or capacitance. You got one, you got the other, in a sense. Okay? I'll see you Friday. If you got questions, please see. Any of the extras, bring them up here too.